You know it's a good day when not even the Python example bot wants to start for you. Hello everyone, it's the cool one, and today we're going to be talking about aerials. We're going to be taking literally the example Python bot, and we're going to be turning it into an aerial mastermind. Next, meme. Okay, the first thing we're going to code is a function, and it's going to be a function that is going to cast global coordinates to local coordinates, or a global vector to a local vector. And as it turns out, this orientation class actually makes this super easy. Simply taking these dot products will create a vector that you can use to essentially, it will essentially create the individual components of our new vector, which will just be the global vector, but casted to local coordinates. One of the things I don't like about the initial bot class is that it doesn't give us any way to work with states. So ideally, you would create like a state machine and you would throw it in here, and then you can enter an aerial state and like give it some initial conditions so that it will hit an aerial. We're too lazy for that, so we're just going to do self.is aerialing. Generally, I like to have 3 states for aerials. I have the align state, where your bot aligns on the ground, and in my opinion, that's the hardest part of the aerial, is aligning on the ground. The second step then is going to be the actual takeoff. I like to have that because sometimes I want to do different takeoffs for different aerials, but that's kind of a bit advanced, so we're not going to be covering that. And then the third state is actually in the aerial, which in my opinion is probably some of the easiest code you will ever write. So in our utils, we're going to quickly create a new file, aerial utils.py. So the first thing that we're going to code is an aerial turn controller. Now generally I would throw this in a separate file called like controllers, where I put like my drive controllers and stuff. But I'm just going to throw it in aerial utils because I'm lazy. Here we're just going to create a few functions. First off, we're going to create an aerial turn controller. And this is probably going to be about 90% of the video, is creating this aerial turn controller. So if you already have an aerial turn controller, you can basically skip this part. Future me, remember to put up a timestamp. Next up, we're going to create a delta v function. And then 3, is kind of just create a function to go for the aerial. And then I'll talk a bit at the end about how to improve our code. Before we do anything, I'm just going to quickly set up our bot with a little bit of state setting. And you can see that we're now having a good old time. There's no hacks going on. We have essentially ascended to the next level, as we're going to want to write a bit of code that'll essentially give us random vectors to align to every so often. There's our alignment vector. And since I like rendering, there we go. We now have our little vector. And about every 5 seconds or so, that vector should change. Yep. So we're going to start on our aerial turn controller now. And this is probably the hardest part. So the first thing we're going to do is we're going to essentially cast our forward vector into local. So this first line basically is going to... This first line is going to take the rotation and use it to cast our forward vector into local space. We're going to be heavily using this math.atn2 function. For those of you who don't know, arctangent basically takes a vector, an xy vector, and it converts it into an angle between negative pi and positive pi. Wait, we went forward and up. I'm dumb. So what happened there is I was dumb, and I thought that y was up, but in Rocket League z is up, because if you think about it, right? If you think about it really hard, when you look at your monitor, the z-axis corresponds to the depth, which if you think about it, if you set your monitor like I do in your lap, that z therefore points up towards your nose, and if you're like me and have an absolutely massive nose, then you know that your nose is in the positive z direction and therefore is up. You just have to think about it that way. All right. So the bot is now pointing its absolutely massive nose towards the vector, but you notice that it's kind of wiggling back and forth. It's kind of, well, I think the technical term is oscillating, but I think that the more technical term is the example bot wiggle. So we want to try to get rid of this example bot wiggle because example bot wiggles are kind of not ideal. So this is where the angular velocity comes in. And it turns out, after casting the angular velocity local, get ready for this, the axis that is not listed corresponds to how fast we're spinning. Our pitch angular velocity is going to be the angular velocity local dot y, because y is the vector that is not listed. So we're spinning around the y-axis. And what we want to do is essentially, if you think about it, if you're playing like some game, like I don't know, like Rocket League, for example, and you want to try to, and you're spinning, and you want to try to stop the spinning, you put the stick in the opposite direction. So here's the deal. We're going to set p equal to 6 and d equal to 0.25. You may be wondering where I got those values. We're going to multiply the pitch angle by p, and then we're going to add the angular velocity, or I guess actually technically be subtract the angular velocity, right, because we're trying to go the other way, times d. I wonder if I have the pitch angle backwards. Let's see what happens now. Oh! Oh! Oh, I figured it out. All right, so, okay, the reason why it was being so weird is because I had my pitch angle backwards. It also turns out that I have my vector backwards, but that's literally as easy as flipping two signs. And bang, we now have a PD controller that is kind of working. Hey, look at that. For the yaw axis, we're literally going to do the same thing. So with the code that I have set up, it's kind of just doing this weird spinny thing, which suggests to me that either P or D is backwards. So what I like to do is I like to set P to 0 and see what happens. And what happens is it just starts spinning. That means that our angular velocity needs to be subtracted instead of added. And now the fact that it stops means that we are good. So I'm going to add the P back in. And it's properly aligning on the yaw. And like just use that. Yeah, no, the D kind of has to be smaller. All right. And this can probably be fine-tuned a lot more, but I don't feel like fine-tuning it, so... So now that we have the bot turning, we have officially completed the hardest part of this entire thing. So, here are the kinematic equations. It's actually pretty simple. So basically, all movement that is some form of acceleration can be expressed as a quadratic function. A equals 1/2 the acceleration. B equals the initial velocity. And C equals the initial position. So starting from this kinematic equation, we end up with A equals 2 times D minus V times T divided by T squared. And that is the equation that we're going to use. So this comes out nicely to this equation right here. Displacement, it's literally exactly what we wrote. 2 times the displacement minus the initial velocity times time divided by time times time, which is a fast way of writing time squared. And we do that for each axis except for z. On z, we also need to subtract the gravity, so that way we're essentially this equation assumes no other forces or no other accelerations being applied. So if we subtract gravity from this final thing, then essentially that's kind of like if we think of gravity as an acceleration, subtracting gravity is adding another acceleration that is opposite to gravity, which basically turns this into zero gravity. That's how I think about it. Basically, this entire function is all that you need to know in order to get your aerials working. And that's why I say that aerials are easy, because aerials are basically fully contained within this one function. We're going to be looking at two things. We're going to be looking at lock equals physics dot equals s dot physics dot location. We're also going to be looking at the game seconds. If the length of that vector is less than 10,060, which is the approximately the thrust from the rocket engine, then the aerial is possible. So this is basically when the aerial starts, as soon as we have a target location to hit. And then if we are already aerialing, all we have to do is we take our align car 2, and instead of the alignment vector, we point it at dv, and dv, of course, this is our delta v function. And that is, I think that's all the code. Oh, look at that. Did you see that? It's doing stuff. All right, we also need to do the boost. So self.controllerstate.boost. You also want to be feathering the boost. And people are like, oh, I don't know how to feather the boost. And yeah, it's actually not that hard. All you have to do is just, if your delta V length is, if your delta V length, in other words, the delta V that you're actually calculating, because you're constantly updating your delta V to make sure you're pointing the right direction. If its length is greater than the dv length that you calculated, that means that you need to boost. And if it's smaller, that means you don't boost. It's that simple. So we just do self.dv length. Holy cow. The mad lad. Oh my goodness, it's actually working. This is insane. Does this bot want to jump off the wall? Look at that! It's working! It's aerialing. Kind of. That we can fix that wobble later. And there you have it. Our bot is now successfully aerialing. Like a lot. Look at him, he's so happy. He's just flipping along, hitting the ball perfectly. He's getting flip resets as well. Like I need to up my bot's game now, because my little example aerial bot that I made in like 2 seconds is getting more flip resets than like any other bot that I've made. Look at that. He's just okay. I did want to talk about how this can be improved further. So a few things. Number one, you can improve this further by messing with the offset. What is it doing? Well, this is an improvement that can be made. Make it not turtle. The currently the bot kind of doesn't really properly simulate forward in time. Currently it uses the delta V, which is fine, but ideally you would essentially calculate the delta V after doing some form of takeoff. Instead of flying directly to the ball, you can fly to the ball with an offset, and you can calculate that offset based on the hitbox, which is what I do in Bowtie. That's actually one of the big differences between Bowtie / Team Dapper aerials and aerials, for example, in Penguin Bot and Beetle. So that Penguin Bot and Beetle just kind of used a blind offset of around 150 or so, or like 120. And that kind of works for most things. But with Bowtie, I wanted to have a really high accuracy aerials. And the best way that I found to do that was basically to calculate was essentially to calculate the actual offset based off of the car's orientation. And that really worked out a lot, so highly recommend that. You can also change the offset to try to make it hit the ball in specific directions. Right now it kind of just gets to the ball and doesn't really care where it hits it. You might want to make it flip like right before hitting the ball if you have that ability, or like make like fast aerials. Okay, I think that's everything. Thanks for watching. I will post this code on GitHub so that hopefully you can start adding aerials to your own bot.